Alright, so this is going to look a little different than in class because I played. So this chapter is focusing specifically on electromagnetic radiation, or this video is, as part of our study of atomic structure. As we saw in class today, you can be looking at a variety of different things with the electromagnetic radiation, all the way from gamma rays, which are given off as part of nuclear decay, or radio waves that we listen to at our homes. And light falls in that spectrum as well. Typically it's a little below 400 nanometers all the way up to just a little above 700 nanometers. But that we have wavelengths in various ranges from one end to the other, and that their wavelength and frequency are directly related to one another. That if you know the wavelength, you can determine the frequency and vice versa. As we saw in class today, this is an inverse relationship as opposed to a direct one, and we'll talk about how that comes about in the next few slides. And so when we look at radiation and we're looking at light, it has been determined over many experiments that this is a result of oscillating wave-like patterns as opposed to specific set movements. And so this led to the study of possibly having light having properties of both waves and matter. So we've seen that wavelength and frequency are connected to one another, and they are connected through speed. That if you graph a set of waves, that the wavelength would be determined by the distance traveled between the two peaks of those wavelengths, or the two troughs, and that the frequency is how fast the waves appear, and that if you were going to graph wavelength versus frequency, or the inverse versus frequency, you would get the speed of light. That is a constant, and I told you it was just 3.0 in class, but I don't want you to get too stressed out about using that for your significant figures, because it actually can go out many, many, many decimal places, similar to Avogadro's number and Planck's constant. So please do not worry about the speed of light having an effect on your sig figs. So as we saw in class today, you can relate the frequency to wavelength using one of those mathematical triangles. Frequency is often written in hertz. That's just the relationship 1 per second. Wavelength is represented in meters, but because we tend to be dealing with the visible spectrum, we're going to be dealing with more nanometers, and then those together give us the speed of light, 3.00 times 10 to the 8th. Okay, and again, this is just a picture showing you that as the wavelengths get shorter and shorter, the frequencies get larger and larger. Just to kind of get an idea of the context of the size, you've got the approximate scale to kind of give you some connection to more practical, everyday substances. Obviously, with the X-rays and the gamma rays, that's not super applicable, but it gives you an idea at least on the larger end of the scale. All right, so this example is going to look at wavelength, determining the wavelength given a frequency. You should be able to do this and go vice versa. We have an FM radio station that's broadcasting at 99.5 megahertz, or 99.5 times 10 to the 6, hertz. And we want to calculate the wavelength. So if we use our triangle, we should be able to see that wavelength is equal to the speed of light over the frequency. We know what the speed of light is, 3 times 10 to the 8th meters per second, and we want to convert megahertz to hertz so that we will be able to cancel out our seconds. Since 1 megahertz is 1 million hertz, that would be 99.5 times 10 to the 6, 1 per second. And so the seconds both cancel out, leaving us with meters over 1. And when we divide these together, I know in class I said just do 2 sig figs because of the speed of light, but again, I don't want you stressing out about the speed of light having an impact on your calculations. So when I went through and did this again, I got 3.02 meters was the wavelength in which the radio waves would travel. So towards the end of the 19th century, again, you have to kind of keep in context that this is before we really knew what was going on with the atom. We hadn't quite developed the quantum mechanical model. We looked at matter and energy as two separate things. Matter was particles. Energy that was in the form of light was described as a wave, but you could not kind of overlap the two. We now know that is the case, but what we're going to look at next is just kind of different different pieces of scientific information that were developed over many experiments that allowed us to connect these two together. So the first one is Planck, that you could move energy in specific units called quantums, and that led to developing the planetary model from Bohr. And so I'll show you there kind of what would happen if you had an absorption of a photon and if you had an emission of a photon. And we see that that energy change can be directly related to the frequency. It can also be inversely related to the wavelength. And that was developed by determining how many joules seconds would be needed to get from the energy to the frequency, or the energy and the speed of light to the wavelength. And so you have that constant 6.626 times 10 to the negative 34th. Again, that's a value that would always be given to you, and it does have more sig figs than that. So again, the constant should not affect your significant figure calculations. So as we talked about in class, this would be what your triangle would look like if you were trying to relate the energy to the wavelength. And then obviously if it was energy to frequency, it's just all multiplied together. We also learned through Einstein that you can relate energy to mass, and that the photons that we've been talking about, if you look at that picture, you see how the waves are kind of moving through, and then as you start to connect the wave and particle idea together, you can kind of have them overlapping together, and you could also look at it from the particle side, working your way across. So basically the two overlap one another, and with that in mind, we can relate the energy of a particle, a photon, to its mass. And because joules is determined in terms of kilograms, that would be relating it to a mass in kilograms. And then finally we had the one with de Broglie. And de Broglie kind of took Einstein's idea and the idea of momentum, and I'm not going to get into this too much because this is more of a physics thing, that you could relate the mass to the wavelength. And when you do that, because momentum is dealing with velocity, the speed of light actually just cancels out. I didn't feel like I did such a great job with this today, so I wanted to kind of touch on this again. And that it will be, the wavelength will be related to the mass of your particular photon as well as the speed at which it's traveling. And again, it's because we're connecting energy from the relativistic perspective along with the electromagnetic perspective, and trying to connect those two ideas together. And because we can relate energy to the speed of light from both sides, we can relate momentum to the Planck's constant over the wavelength. And that gives us, when we connect those together, since momentum is mass times velocity, that the wavelength would be equal to Planck's constant over your mass in kilograms and velocity. Diffraction is one way in which we can kind of verify this idea that matter has properties of waves and particles, like it's scattered. It's how we get that rainbow effect, especially if we've had like a rainstorm and you see the rainbows, or you see what appears to be a rainbow-like image on puddles of water. Different substances will make different X-ray diffraction patterns. And we can only kind of look at those X-ray diffraction patterns by looking at them through waves. You can kind of see more of the wave-like pattern in this spiral, which we often see in tie-dyes. And because it can do that, and we know that atoms and ions have specific amounts of matter, well, light must have matter as well, and must act as have particle-like features just as much as it does waves. So this picture here is just showing what happens when you X-ray a sodium chloride crystal. You will get a variety of a pattern in terms of the diffraction that you see. Where it is bright, it's because you have overlapping peaks, and where it's darker, you see that the trough from one wave and the peak from another are overlapping, and that causes it not to be as strong and a little bit darker in certain areas of the diffraction pattern. And so putting these ideas together, we've already talked about how delta E can be related to hc over lambda, but we can look at this for specifically a photon in terms of both of its energy and in terms of its mass. And so no matter where you're at on the electromagnetic spectrum, Whether you're a radio wave, whether you're a gamma ray, whether you're a visible ray, or whether you're an infrared ray, you have energy and you have mass. So a photon of ultraviolet light possesses enough energy to mutate a strand of human DNA. What is the energy of one UV photon and then a mole of UV photons that have a wavelength of 25 nanometers? So we have a wavelength, we want to find energy. And so if we use that triangle, delta E equals hc over lambda, we get that lambda is equal to hc over delta E. I'm thinking we're solving for wavelength. Sorry guys, we're solving for energy. It's been a long day. So you have your Planck's constant, you have your speed of light, and you do need to change your wavelength to meters because your speed of light is in meters. Remember that 1 meter is 10 to the 9th nanometers. So that's how I got that converted. The meters go away, the seconds go away, and when we multiply and divide, our sig figs are going to be determined by the wavelength precision, which is 25 2 sig figs. So per photon, we have that the energy change would be 8 times 10 to the negative 18th joules. That is not a lot of energy, but we're dealing with something very small, very tiny. But if we wanted to do it with a mole of photons, well, 1 mole would have 6.02 times 10 to the 23rd photons present. So we can relate that using Avogadro's number. And when we multiply Avogadro's number times that 8 to the negative 18th, we get that there's a fair amount more energy that would be released, 4.8 times 10 to the 6 joules per mole, or 4,800 kilojoules per mole of photons. In this next example, we're going to go in from the opposite perspective. We're taking the energy that it would take to remove 1 mole of electrons from the surface of a rubidium metal. Its ionization energy, 208.4 kilojoules per mole. And we want to know how much energy it would take to remove 1 electron. So before we went from the photons to a mole of photons. This time we're going from a mole of electrons to just 1 electron. So we have the moles of electrons, and we know that 1 mole of electrons contains 6.02 times 10 to the 23rd electrons. Mole just represents an amount. So when we divide this time, we get that the energy that would be needed to remove 1 electron is fairly small, 3.462 times 10 to the negative 22nd. We now want to find out in the second part of the question, what would be the maximum wavelength of light that could do this? Well, if we know our energy change for that particular electron, we should be able to find the wavelength. Lambda, our wavelength, would equal hc over delta E. We know our h, our Planck's constant. We know our speed of light. And we now know the energy change associated with removing 1 electron, 3.462 times 10 to the negative 19. Note that I changed from kilojoules to joules so that the joules would cancel out with Planck's constant. You do need to make sure you watch out for your units, especially those of you who don't like to write them. The joules would cancel, the seconds would cancel. We multiply and divide. We are limited in terms of sig figs by the amount that's present in our energy. Again, the speed of light will not affect your sig figs. And so that would give you 5.742 times 10 to the negative 7th meters. Because we typically are dealing with wavelengths in nanometers, especially if we're dealing with visible light. 1 meter contains 10 to the 9th nanometers, so that would be 574.2 nanometers. And the last example we're going to do for this video is involving neutron diffraction. This time we're going to be dealing with de Broglie because we're relating the velocity to a wavelength. You can do that. You can relate the mass in a wavelength to its velocity. From now on, I'll always put in there that you're dealing with de Broglie wavelengths, so that way we won't have too much of an issue. If we go back to that de Broglie equation where the wavelength is equal to the speed of light divided by the mass of your particle times its velocity. We want to find velocity, so if we cross multiply and isolate the velocity, we would get that it is equal to this Planck's constant over the mass times the wavelength. Again, we know that Planck's constant is joules times seconds, and because we're dealing with mass, which is not going to have a joules component, and wavelength, which is also not going to have one, going to go ahead and switch it over to the metric fundamental units that were used to create the joule so that you can see where the units are going. So 1 joule is equal to the mass times a distance unit squared over a time unit squared. Because Planck's constant is joules times seconds, when I multiply both parts of that equation by seconds, I cancel out one of the two. So velocity for this particular neutron would be equal to 6.626 times 10 to the negative 34th, and then the units that were remaining down here, kilograms times meters squared per second. The mass of a neutron is not something I expect you to come up with. It's a constant. It's in your text. They will be in problems from here on out, and you could Google it if you really needed it. But that is not something I would ask you to come up with. So that's that 1.67493 times 10 to the negative 27. Lots and lots of sig figs because, again, it's not supposed to affect what you report your answer to when it's all said and done. Picometers is our wavelength, and our Planck's constant is in meters. So 1 meter contains 10 to the 12 picometers. So when we convert it, that gives us 7.5 times 10 to the negative 11. The kilograms cancel. One of the meters cancels, and we're left in units of meters per second. Velocity tends to be in units along those lines, some sort of distance unit per time. So when we multiply and divide, we want 2 sig figs in our answer due to the wavelength sig figs, and that gives us a speed of approximately 5,300 meters per second. And that should get you through the problems for the electromagnetic radiation section of this chapter.